All. Thank you for attending this session. My name is Pooi from the School of Material Science and Engineering in the Nanyang Technological University of Singapore. So first of all, I'd like to thank Eileen for inviting me to give this talk on the augmented one-dimensional nanostructured sensor elements. I'm sorry, on my throat, there's a problem. So today I'd like to discuss on the ways on how we make hierarchical structures as well as nanostructures using a hetero mechanism, as well as using such a nanostructure in electronic applications for sensors. For example, in gold nanoparticles assembling onto the nanowire, as well as doping of zinc or copper into indium oxide nanowires and core shell nanowires of zinc oxide and indium oxide. And then we would like to discuss about the sensing mechanism as well. So as we all know, for metal oxides, it is a wide bandgap semiconductor for some of the metal oxides, including zinc oxide, indium oxide, and tin oxide. So the advantages of such oxide is that they are very stable, having unique optical and electrical properties. They are able to give properties such as gas or light sensing for energy conversion, field effect transistors, and light emitting diodes. So this rich family of nanostructures give very versatile applications as well as properties. For example, they can be assembled into core shell structure or in the alternating heterostructures or three-dimensional structures, like just now the keynote speaker in the morning session was talking about three-dimensional hair mimetic structure. I believe this can also be done using a nanowire as well, not just using the top-down approach. As what we can see here, the nanostructure, apart from binary, we can also make them into ternary oxide nanostructures. For example, into three-dimensional assembly or in a very parallel arrays, as well as you can tailor them using a 2D assembly into thin films. So in my group, we are keen in making use of such nanowires for photodetectors as well as electroluminescence, for nanowire sensors, and also for electrochemical devices. So for today, we will focus more on the sensors applications. So first of all, we try to think how we can make unique nanowires using the chemical vapor approach. So in this nanowire growth, we try to alternate or perturbate the vapor during the growth. So what happens here is that we are able to change the direction of the growth due to the perturbation of the pressure. So the gas flow rate here is about 20 SCCM, and then during the on, which is a high flow rate, it's about 200 millibar, and then we reduce the pressure flow rate to around 0.03 millibar, and each cycle for about 5 minutes for 10 cycles. So we are able to tailor like the changes in the direction of the nanowires along 100, and then it will switch the direction to 110 transition. So over here, there are two types. One is that along the main branch, it is tailoring and changing in direction. The other one is that the nanowires on the main core mother nanowires, then the child nanowires, they can also change in terms of the direction in growth. So these nanowires, when they met to the center nanowire, again, they can be welded at the contact region here. So once the welding starts to occur, you can see very high crystalline structure. There are no defects upon the nano welding. So this shows that we can actually form nano ring structure based on such approach. So we are very keen to continue to explore on how we can very systematically and very in an organized manner, how we can make such a nano ring structure. So apart from that, in the hierarchical oxide nanowire growth, we can use two types of mechanism. One is based on homoepitaxial growth. Over here, we demonstrate a ternary oxide, which is based on indium germanate oxide. So in this case, the homoepitaxial growth is referring to having a mother nanowire and a child nanowire the same composition. So these are typically done by a combination of vapor solid as well as vapor liquid solid growth mechanism. So very often these are based on the nanowires that are grown on a polygynous microcrystal that has the same composition that allows the alignment of the nanowire and giving a homoepitaxial growth in a gold-mediated vapor solid secondary growth mechanism. On the other hand, we can also make use of heteroepitaxial growth. In this case, the child nanowire and the mother nanowire, they are two different compositions, but of a very close lattice matching. So in this case, for example, the secondary deposition of zinc oxide, which is on top of a zinc germanate oxide, would give a heteroepitaxial growth. The reason is that these two types of nanowires that have very close lattice matching of less than 3%, and they have very close crystallographic structure. So what we can see here, a three-dimensional zinc oxide branch with a six-fold symmetry can occur with a direct vapor solid deposition. And the deposition condition is for the zinc germanate nanowire formation is at about 1,000 vaporization and then collecting at about 400 to 500 degrees Celsius. So the formation of such heteroepitaxial growth is due to the small lattice mismatch, as we have mentioned, and we have the rectangular crystallographic plane of the zinc germanate nanowire in a 1 bar 0 plane, and this has very close lattice matching with the hexagonal zinc oxide 001 plane in the multiplicity of a 6 to 1. So as we can see here, in the direction of 001 of zinc oxide as well as 1 bar of a 1 bar 0 of zinc germanate oxide. So the close lattice matching between these two would allow a very epitaxial growth promotion at the interface. So this we try to capture at the very initial phase how the zinc oxide nucleated on the zinc germanate nanowires. So on the other hand, we can also grow at two-dimensional nanowires in the nanoribbon form. This is usually promoted by a two-dimensional nucleation probability that is governed by not just the surface energy, but the supersaturation ratio, which is much more important during the growth, as well as the growth temperature. So over here, we use the amount of oxygen to control the growth of the ribbons. So the oxygen concentration is about 5 to 10%. And we noted that the higher growth temperature as well as a higher supersaturation ratio would allow us to increase the two-dimensional nucleation probability, giving us the 2D nanoribbon structure. So the 2D ribbon structure actually would give us a very good platform to study the transport mechanism as well. So these are some of the examples of high-resolution TEM of how the 2D nanoribbons will look like, and they are typically also in a single crystalline structure. So we have made use of such ternary oxides to sense light. So this is called photodetector in light sensing. So we shine light and then it will show a difference in the current responsivity. So the amount of carrier circulated during the absorbed photons per unit time is called the quantum efficiency, and it gives a very high responsivity as well for such indium germanate nanowires. So a very high photoconduction can be occur, and this is typically for one-dimensional solar blind photodetector. The reason is that the wavelength that we're using here is 230 nanometer. It's well below the UV light region. So we can see here very fast sensing response of less than 0.3 seconds can be achieved. Also having a relatively good signal to noise ratio, and with light pulsing, it's also very repeatable. So we are keen to explore such nanowires for gas sensing applications. There are two types of gas sensing possibility. One is the conductometric sensing. The other one is the single nanowire based on field effect transistor. So a lot of our effort is focusing on the field effect transistor. The reason because this allows us to measure the sensor at room temperature as well as can give us a high sensor response as well. So over here in the field effect transistor, we are using the backgate contacts. As you can see here, the gate electrode is at the bottom, the dielectric followed by the source and drain connecting the nanowire. So a lot of times we also use FIB for connection, or sometimes we just use the contact as it is. So these are some typical examples of indium oxide field effect transistors. The IDVG curve showing a high on-off ratio with a good subthreshold slope, and the IDVD curves at different VG. So these field effect transistors are relatively compatible with some of the thin film transistor as well. So the subthreshold region is very important because it gives us the optimum sensitivity for a nanowire field effect transistor sensor. So the example here given is for 2 ppm NO2 sensing. So this is the sensor responsivity. As we can see here, typically it will have a higher responsivity at the subthreshold region, meaning that we may need to apply a gate voltage of up to 20 volts here in order to get the best sensor performance. So the mobility of such nanowire is about 139 centimeters square per volt second. So this finding of having optimum responsivity at the subthreshold region is similar to one of the pH sensing work that was published earlier in 2010. What they found is that, as we can see here, the subthreshold region, when they use the VG at the 0.2 volt, which is at the subthreshold region, the conductance or the sensor response is much better compared to the linear region or near threshold region. So this is something that we should take note. Apart from that, the contact modulation is very important as well. So there are two types of contacts that are possible. One is on the ohmic contact. The other one is on the Schottky contact. So ohmic contact can typically be formed when we form a very good contact using the nanowires that are embedded between the two electrodes. On the other hand, Schottky contacts are very often found when the nanowire is just dropped on top of the gold electrode. So this is formed when indium oxide is embedded under the chromium with gold electrode, and whereas for the Schottky contact, the indium oxide nanowire is typically formed on top of the gold electrode. So these two types of contacts will give us a different sensor response as well. So the kinetics of the gas and surface reactions are very important, especially it is governing the electronic interaction. Apart from that, the surface reaction kinetics also dependent on temperature, pressure, and the vacancies of the nanowires. As we can see here, in the Schottky contact, we measure at various temperature. Then we are able to extract the barrier height. So this barrier height is very close to the barrier height of gold with indium oxide. So this also gives us a thermionic emission current injection. So we make use of these two types of contacts. One is the ohmic contact, and the other one is the Schottky contact. And then we measure two types of gas. One is the CO gas, which is the reducing gas, and the other one is the oxidizing gas or NO gas. So we realize that the reducing gas or CO gas is much more sensitive for the Schottky contact. Meanwhile, for the oxidizing gas or NO gas, it has a better responsivity for the ohmic contact. So the reason being, for ohmic contact, the contact resistance is very low. So the surface kinetic during the gas adsorption is playing a more dominant role in the ohmic contact. So in this case, for the oxygen adsorption, it is governing the whole reaction kinetics. So it is much better for the oxygen or the oxidizing, in this case, the NO gas, to have a much better responsivity. On the other hand, for Schottky contact, the energy barrier is dominating the device responses because in the Schottky barrier, it has a certain barrier height. So during the absorption of the reducing gas, the CO gas is contributing electrons, and therefore it is changing the depletion region. So in this case, the Schottky contact is much more important for the CO gas or reducing gas. So in order to increase the sensing responses, we also try to enhance the sensitivity by introducing nanoparticles. So in this case, the introduction of nanoparticles onto a nanowire can be done using two ways. One is that just using physical absorption of the nanoparticles or nanowires. In this case, it will not be very controllable, as well as the density will not be very high. So we try to use an approach of a self-assembled monolayer in order to capture the nanoparticles onto the nanowires. So in this case, this is done by, first of all, after an hydroxyl treatment, we use a SAM layer, which is a self-assembled small molecule of APHS, having the NH group as well as OH group here. So at the end, these groups would be captured onto or adsorbed or chemisorbed onto the nanowires. And the gold nanoparticles that has been synthesized has a negative charge with a citrate group surrounding it. So it has very good electrostatic interaction with the NH2 group. So using this, we are able to functionalize the gold nanoparticles onto the nanowires here. So in this case, you can see enhanced gold nanoparticle density can be achieved using such self-assembled monolayers. So we noted that the IDVD as well as the IDVG curves can also be measured from these gold nanoparticle functionalized nanowires. So in fact, the nanoparticles density can also be changed by the immersion time of the nanowires onto the gold colloid solution. So similar to the self-assembly on thin films, it can be tailored by the immersion time. After about 1 hour, the gold nanoparticle saturation is almost there. We do not see significant changes after which. So we can tailor from 10 minutes, 20 minutes, 30 minutes down to 60 minutes, and quite a substantial increment in the gold nanoparticle density or loading of the gold nanoparticle can be achieved. So these are some of the high-resolution images of the citrate stabilized gold nanoparticles colloids that are about or less than 10 nanometer, as usual. And we can see here the CO sensor response comparing the ones with a SAM only without the gold nanoparticle. And this is with SAM as well as 10 minutes of gold nanoparticle loading. There is a substantial improvement in the sensor response compared to the one that has only the SAM layer. So the SAM layer, we noted that it does not change much compared to the one without the SAM. So it doesn't contribute to the sensor response. Whereas the gold nanoparticles, as we increase the loading amount, it is increasing the sensor response dramatically. So these are some example of the sensor response for different concentration of CO gas. As we can see here, up to 5 ppm, it is increasing in terms of the gas sensor response. A maximum sensor response of up to 110 for 5 ppm of gold, 5 ppm of carbon monoxide for after the gold nanoparticle functionalization can be achieved, which is referring to this. It is 60 minutes gold nanoparticles immersion. So on the other hand, if it is just a physical decoration, which means it's without a SAM, then the sensor response is very low. So it's only about 4.5 over here. So this can be understood apart from the high surface coverage of the gold nanoparticle after functionalization. So the CO oxidation of the gold nanoparticle on the surface is very important when it increases the nanowire conductance. As we can see here, below the nanoparticles, we have a SAM layer, and it has a depletion zone underneath the gold nanoparticles here. So this metallic nanoparticle, typically it will have a catalytic effect. So this catalytic effect, it increases the oxidation rate as well of the CO gas when they're being absorbed onto the nanoparticle. So this coupled with the presence of the Schottky barrier that is at the junction, it helps to create a very sensitive device. So comparing here, this is without catalyst, this is with catalyst. We believe that there is an intermediate state that gives us a much faster kinetics in terms of enhancing the sensor responses. So in this case, there are some a proposal as well that is given to some noble metals for interaction with gaseous phase on the metal oxide. First of all, the oxygen, for example, can absorb onto the defect states, and then there is some catalytic dissociation because of the presence of the nanoparticles. And these are weakly adsorbed molecules that will move along the nanowires, and ultimately they will form two types of a collection zone underneath, depending on the change or modulation in the resistance. So this resistance region, it's governed by the diffusion layer that is formed underneath the nanowire, as well as the ones that is adjacent to the nanoparticles. So because of the combination of these two effects, it improves the sensor responses. So now I'd like to move into doping of the nanowires. So first of all, the first doping that we have studied is the copper doping. So this copper doping during growth, a less than 5 weight percent is being incorporated. And after that, we try to use the DEP or dielectrofluorescence to arrange the nanowires. So after arrangement, then we try to build the FET. So we can see here, these are the copper dope indium oxide nanowires, and they follow the cubic structure based on the Raman spectra of the indium oxide crystallography, and typically a single crystalline can still be maintained after the doping. So based on the XRD, there are some moderate shift because of the smaller radius of the copper ions that are being incorporated or substituted into the cubic phase of the indium oxide. And if we noted that there are also slight rate shift of about 0.5 electron volt based on the reflectance spectra. This is because of the hybridization of the 3D as well as the 2P of the indium oxide and copper in this case. So therefore, compared to the indium oxide, which is having a band gap of 3.6, this is slightly reduced in this case. So a barrier height of about 0.39 electron volt can also be achieved. Excuse me. So we can have a pretty good subthreshold slope of about 200 millivolt per decade, giving a mobility of 86 centimeters square per volt per second. So based on this, so we try to use the copper dope indium oxide compared to the pure indium oxide. So the copper dope indium oxide gave a very good sensor response compared to the undoped ones. However, we noted that the responsivity is very slow. Thank you very much. It's very slow. It's about 50 seconds recovery here when we are using the copper. We believe that this is because there are some defects that are present at times. So after the absorption, it may not be very easily recoverable. So this copper dope, when it is present in the indium oxide, apparently, it is also acts as the center that is capturing the electrons because of a p-type nature. So it is enhancing the responsivity of the CO gas sensing. Then we try another type of doping. Sorry, give me a minute. So the other type of doping is the zinc dope. So in zinc dope, we noted that the quality is much better. It has much better recovery time, faster right now compared to the copper dope. So this is using the FET as well, before and after exposure. So we noted that it has very good selectivity as well. Like the selectivity is much higher for CO gas compared to NO or NO2 gas. So in this case, the zinc-doped indium oxide can serve as a very good platform for us to change the selectivity of different gases. Well, such as zinc-doped nanowires, we have also tried to use them for resistor-based sensing. So in resistor-based sensing, what we have done is that we can measure them at different temperature as well. But what we did was just to detect the changes in the resistance. So for example, over here, comparing a different type of gases ranging from CO, NO2, ethanol, and hydrogen. So most likely, the reducing gas like CO, ethanol, as well as hydrogen gives very good sensor response for indium zinc doped nanowires, whereas the NO2 shows better responses for the indium oxide nanowires. So in this case, when we plot the sensor response, that over here, it's obvious that NO2, which is an oxidizing gas, is showing a much better performance for indium oxide, whereas the rest, which are reducing gas, has a better sensitivity when zinc is being incorporated, because the reason is that the creation of the oxygen vacancies and the surface defects enhances their receptor functions for such a reducing gases. So we also tried the heterostructures of using zinc oxide that's coated, surrounded the indium oxide nanowires. So such as zinc oxide, when they are coated as the shell onto the core of the indium oxide, they are polycrystalline and grainy in structure. And then we try to make them onto the heater using the resistor plate method. So this resistor-based sensing is measured at various temperatures to optimize the sensor responses, and these are the optimum conditions for different type of gases at various working temperature. And we realized that for reducing gas, similarly, they have also a better performance for the reducing gas using the core shell structure, whereas for the oxidizing gas, it's still the best for the undoped indium oxide nanowires. The reason being, we have an integrated barrier height here, not only just between the along the nanowire with the contacts, but also between the nanowire and nanowire. There are several barrier heights that the gas or the electrons need to transverse when they want to have the interaction with the nanowires. So in this case, for reducing gas, it is reducing the depletion region when it is being exposed, but these are only limited to the surfaces. But for oxidizing gas, at times they even have a large integrated enhanced elongated depletion layer, and therefore it's much difficult to withdraw the electrons from such a system. So therefore, the sensor response is poorer for oxidizing gas. So with that, I conclude by giving an outlook and summary. The augmented one-dimensional nanostructures is very good for enhancing the sensor responses. This includes the using of nanoparticles, doped nanowires, as well as heterostructures nanowires. And particularly the assembly and the design of such nanowires are very critical. So we do hope that there will be much more collaboration with different groups. And particularly, I'd like to mention the collaborator for this work is with Brescia University, Professor Elisabetta Comini, and as well as Dr. Andrea Ponzini. And I'd like to thank my group members as well. Thank you very much, and I apologize for my bad throat today. Thank you.